This is Bharat. So today we'll start solving problems on wave theory, electromagnetic wave. So if you see the question says there is an electric field which is traveling in a free space. So first of all, a free space simply means there is no medium at all. It's a vacuum you can think of. So free space parameters are defined like this. So epsilon r means the relative permittivity and relative permeability are taken as one. Means epsilon is nothing but epsilon naught into epsilon r, and mu is equal to mu naught into mu r. So if I take these two as one, then epsilon is simply equal to epsilon naught and mu is equal to mu naught. So here if you see an electric field is given with 50 times cos volt per meter. So first of all, what is the direction of the wave? Of course, you can easily guess it if you have a practice of identifying the waves. Because already in the class we discussed like the general format of a wave looks like a cos omega t minus kz for a wave traveling in positive z direction. But of course, here there is no z or anything. So let me walk you through how do you identify the direction. Right? Always your wave is a function of space and time. So your wave electric field should be a function of space and time, right? So if you see this function, this is given here, right? So it's not a function of y, it's not a function of z, but what I can see, it's a function of x and it's a function of time. Obviously, it's a function of time, and the time is varying like cos of 10 to the power of 8t, in which this factor looks like omega, and the frequency means if you put x equal to 0 in this equation, we get cos of 10 to the power of 8t, which is a signal which varies with time. So this omega should be equal to 10 to the power of 8, right, radians. So if you see, it's only depending on x and t time. Of course, the time variation there, it is depending on x. But this x contribution is not for the magnitude, but in fact it contributes to the phase, right? So the magnitude, this 50 is not a function of x or y or z, right? It's a constant, obviously. So you can see the magnitude is not going to change here. Only thing that changes is the phase of this cos is a function of x, and how fast the phase changes in x direction is given by this beta factor. So when you write beta into x, just like when you write omega into t, this omega says how fast the signal is varying in time. In a similar way, the beta indicates how fast the signal is changing in the spatial domain. So this we already discussed, but let me try to understand the wave here to see what is the direction of the wave. Okay, what we can do here is if I draw a t equal to 0, the same electric field looks like 50 times of cos beta x, of course a y cap direction. If I take the magnitude of it, I don't get the vector, so it is 50 times of cos beta x. So if I draw it, it's simply a cosine wave, right? It's a cosine wave. Let's say it's a cosine wave, and it's varying. So this is x, it's not time, it's x. So along x-axis, the magnitude is oscillating between 50 and minus 50, and it's spatially in this format. At t equal to 0, I can see. But say for example, if I take some t as non-zero function, say t is not equal to 0, maybe I'll take t is equal to some 2 seconds, right? If I take t is equal to 2 seconds, the same signal looks, the magnitude of the signal looks like this, 50 times of cos of beta x, right, plus 10 to the power of 8 into 2 seconds, right? So if I see this, there is an additional phase shift. right? I can see that this is something like a function. If you have an f of x and you shift it, if you do an f of x plus a, what does it mean in signal systems? You have read it already. It is like shifting to the left, right? So as you increase this a, it shifts more towards this direction. Okay, so this wave is going to shift in this wave as the time is going to increase. So I can say it's propagating in negative x direction. So the disturbance here, the disturbance in electric field is propagating in negative x direction. Okay. So that is done. So we'll go for the next one. So usually the thing is, the general format is like cos of omega t minus whatever the spatial variations, you get a beta here. If it's a wave going in x direction, you get a minus x. If it is a plus x, that indicates that it is actually a wave going in negative x direction. For example, if it is a cos of omega t minus beta y, this is a wave traveling in positive y direction, right? So this is the kind of general format which we follow. We actually discussed it in the class also. So I'll go to the next question. The next one is we need to calculate this beta. What is this beta? Beta is a name. In fact, it's called phase constant. In this case, particularly beta, you can call it as a beta or k. It's all are equal. Beta is k. This where this beta is nothing but phase constant, or sometimes it's called k, is called wave number, or it has another name like spatial frequency, how fast the wave is changing in space. Alright, many names, but all mean the same thing. So how fast your phase is changing in space, phase constant, a wave number, how many waves are there per unit distance, and spatial frequency, how fast the wave is changing in space. So whatever it is, beta is equal to k. So usually the formula for beta goes out like beta is equal to omega. Sorry. Beta is equal to omega into square root of mu naught and epsilon naught. Of course, the actual formula goes like beta is equal to omega into square root of mu epsilon. But in our case, it's a free space, so the formula goes to omega into square root of mu naught epsilon. So what is the value of beta? So beta is 10 to the power of 8 times of square root of mu naught and epsilon naught. Okay, but we know that 1 by square root of mu naught epsilon naught is approximately 3 into 10 to the power of 8 meter per second, which unit is velocity meter per second. So if you substitute it here, so you get 10 to the power of 8 divided by 3 into 10 to the power of 8. So cancels out at 1 by 3 and the units is radians per meter. So that is the value of beta. So we have the value of beta. So next is, the question asks for the time the wave takes to travel a particular distance. So wave in the sense some kind of distance, it is taking some time to travel some distance, means it should be having some velocity, right? So how do you get the velocity of the wave? Usually if you remember, we have an equation like when we solve the Maxwell equations, we get an equation like 1 by square del square of eta is equal to mu naught epsilon rho square square, right? So this kind of equation we got when we were solving when we solved the Maxwell equations in time domain. I mean, so this is the differential equation we got, and we said the solution to this equation is a wave. In fact, we came to that conclusion because if we have any function with variable with space and time like this, right, and if it satisfies this equation, the solution to this kind of equation is a function which satisfies this differential equation, which is a function of space and time, will behave like a wave means will behave like a disturbance which propagates with some velocity where this v gives you the velocity, right? I think I made a mistake here. This is not epsilon. So it travels with the velocity. So when we calculated the equations in free space, so from here when equating these two, we can understand the velocity of the wave is nothing but, because both looks like wave equation, so the velocity of the wave becomes 1 by square root of mu naught epsilon naught, which is 3 into 10 to the power of 8. So that is why an electromagnetic wave is said to travel with the velocity of light 3 into 10 to the power of 8 meter per second. So you can see we know the velocity because it's free space, we know the velocity. So we are asking how much time it takes. So you can say the magnitude of the velocity is nothing but the distance traveled by the time taken. So it's asking the time. So if you know the distance, you are traveling the distance of lambda by 2 and the velocity is c. So if that is the case, I can write it as 1 by 2 times of lambda by c, but you know frequency is equal to c by lambda. So from there you can write it as half times of 2, or the same thing as t 1 by f is nothing but the time period of the wave, which is by 2, right? So you can calculate the time period, but in fact you can substitute the frequency also here. This is 1 by 2f, I can write it like 2 pi divided by 2 times of omega, because I multiply 2 pi in numerator and denominator. 2 pi f is nothing but omega. You can see it is pi by omega. We have omega as 10 to the power of 8, and you get an answer something like 31.429 seconds. Right. So that concludes the first problem. So we'll go to the next one. So here, if electric field is not given, but the same free space is given, and the magnetic field is given, and is asking you to calculate various parameters here, right? So when we see these kind of problems, you might expect I should calculate the electric field first, because I cannot calculate these parameters from magnetic field. It is not like that. So as we studied, electric fields and magnetic field coexist with each other in a wave. So whatever kind of propagation properties an electric field have, the same kind of propagation properties a magnetic field is associated with. Only thing is the magnitudes and the phases are related by some factor called intrinsic impedance, which we will see afterwards the problems on that. But the only thing, the propagation characteristics are not going to change. What I mean by propagation characteristics in the sense, for both electric and magnetic fields, the direction of propagation is going to be the same, because it is not like electric field will be propagating in x direction and the magnetic field is propagating in negative x direction or y direction. This cannot happen. Direction of propagation, right, is same for both electric and magnetic fields, because an electric field is propagating, associated with it there is a magnetic field. If there is a magnetic field which is propagating, I can say associated with it there is an electric field. So you have a scenario here, direction of propagation is same, and of course propagation constants like attenuation constants and alpha and beta, so all properties will be same, but still we didn't go for alpha and here, but even with the lossless medium free space. So for electric and magnetic fields, but obviously the directions will be different for electric and magnetic fields. We're not worried about the directions right now. So we'll start solving this problem. So first thing here is the magnetic field is given. So what is the direction of the wave? You can see the phase is going minus kx, so I can say it is propagating in positive x direction. It's a wave traveling in positive x direction. So the question does not ask for the direction, but it asks for k. K is nothing but the wave number or phase constant. And you can see, you can see that this number is nothing but omega, because any wave looks like cos of omega t minus kx, right? So omega is here for us. So we need to calculate k. K is nothing but, right. So k is nothing but, right. So what is the value of k? K, or it is simply beta, is omega into square root of mu and epsilon. Okay. But in case it's a free space, it is mu naught epsilon. So I can simply say omega by c, because c is nothing but 1 by square root of mu naught epsilon. So I can calculate c here, but you can see here omega by c, it can be written as 2 pi f by c, or this is nothing but 2 pi by lambda. Okay, so first of all, keep aside this relationship. We'll see what is omega by c. Omega is 2 into 10 to the power of 8 divided by 3 into 10 to the power of 8, right? So you get an answer like k equal to 0.667 radians per meter. So what about lambda? So because you have k, you can calculate lambda, because k is nothing but 2 pi by lambda, or lambda is 2 pi by k. So you have the value of k. If you substitute it, you get an answer like 9.425 meter. So what is the time period? Time period is nothing but 1 by frequency, or multiplied by 2 pi, it is 2 pi by omega. So you have the omega, which is 2 pi divided by 2 into 10 to the power of 8. You get an answer of 31.42 nanoseconds. And the question asks for what is the time taken by the wave to travel a distance of lambda by 8. So distance is equal to, sorry, time is asking. So time is equal to distance divided by the velocity, which is c, right? So it is lambda by 8. Distance divided by c. So it turns out to be lambda by c into 1 by 8. And of course, lambda by c is nothing but frequency by 8. You get time period by 8. So you know the time period, you divide it by 8, you will get an answer like 3.927, okay, nanoseconds. So that is how we solve this problem. It's a bit easy. Simply you need to understand the concepts of wave here, propagation of wave, whether it is an electric or magnetic field, it doesn't matter. We're talking about a wave propagation here. Right. We'll go to the next one. This is a bit easier one. Okay. So the question doesn't ask for any propagation constants or anything. Simply it asks for there you can see that an electric field expression is given, and we are asking you to convert it into a phasor form. The reason behind discussing this is, when we try to calculate the relationship between electric and magnetic fields, it's always better to write the field equations in phasor forms and then solve them. Basically, phasor form is like writing an equations in frequency domain, or you can say writing the equations in complex domain. So that makes calculations easier. So you need to get an idea of how easily you can convert bonds back from phasor form to time domain and time domain to phasor form. So here is your field. I want to convert it into phasor form. So how do I do it? So simply this 100 e power j times of 10 to the power of 80 minus 0.5z plus 30 degrees. Take a real part of it. So what did I do? Basically real part of e power j theta is nothing but cos theta, right? uh, Euler's theorem, e power j theta is cos theta plus j sin theta. So real part of it will be cos theta. So I'm using the same phenomena here. Okay. So if I have a constant, say for example a times of e, I get a cos theta. So I did the same trick here. So it is written like this: real part of. From this, we need to separate the time variation here. So I can write this as real part of 100 times of e power j into 10 to the power of 8 and e power minus 0.5z and e power power minus j into 0.5z and e power j times of 30 degrees. Okay, so when you write a phasor form, you actually neglect this real part and this e power j omega and you write whatever term is left out. So it is 100 e power j 30 degrees and e power minus j 0.5z. So it is like I can even do something even better. So e power j 30 is like cos 30 plus j sin 30. So I get 100 times of 3 by 2 plus j over 2 e power minus j 0.5z. Well, if I do it is 50 by 3 plus 50j into e power minus j 0.5z. So instead of writing this equation, the same equation can be written in frequency domain or phasor domain in this format, right? So you use the same expression like this. So both are same expressions. You might say, sir, they doesn't look similar. There is no time variation or any kind of other variations, but that is why we go to the phasor domain. There we remove the time variation because we know all kinds of sinusoidal inputs gives us a sinusoidal outputs. So there is no need of repeating that sinusoidal variation again and again. So in frequency domain, we don't go for this omega t term. We purposefully neglect that term. Okay, and anytime you can bounce back to this equation again. From this equation to this equation, we'll see that how we do it again. So this is your phasor form. So in your phasor form, your magnitudes can be a complex number. So you need to understand the difference here. So in time domain, the magnitude is a real number, but in phasor form, the magnitude can be a complex number, right? But in time domain, you cannot have a complex number. You cannot have a signal which looks like 100 plus j cos of 10 to the power of 8t minus 0.5z plus 30 degrees. This kind of signal you cannot see. You might say, why can't I, sir? Why can't I see a signal which looks like that? Because this is a complex signal and you cannot generate it practically. But this kind of signal maybe you can generate it. Okay. In steady state you can generate that kind of signal, but this kind of signal is not practical one. These are not real signals at all. But this is a real signal. The output of this signal is always a real number. So but phasor form is not something like it's not a practical value. It's a mathematical. I can say anomaly mathematical similarity of time domain, which is created in frequency domain. So and you can see here there is a time variation. Here there is no time variation, and minus 0.5z indicates a wave traveling in positive z direction. You can see that is influencing here, which shows a phase variation. So this is the phasor form. We'll go to the next one, which you can see that here the electric field is given, and the field is not in time domain, but it is in phasor form. And you can say, so the electric field is having many components. What should I do? You don't have to worry about it. Electric field is a vector, and the magnitude is a wave. Right? I mean, not the magnitude means each individual components will have a wave kind of format. So how do you convert this equation into time domain. So the frequency is given as f is given as 1 megahertz. So 10 to the power of 6 hertz. I can say omega is 2 pi into 10 to the power of 6. So the simple thing is you take this electric field equation. So whatever electric field you have, you multiply it with e power j omega t. So 100. Sorry. Hundred. At an angle can be written as e power j 30 degrees. X cap plus 20 e power minus j 50 degrees plus 40 e power minus j 220 degrees. So this is a polar form representation, some magnitude and an angle. The same thing can be written as like this: 100 into e power j 30, of course, for a cap and z cap. So you multiply this whole number with e power j omega t, take real part of it. Right. So what happens if you do a real part of it? So first of all, let me rewrite this expression like this becomes 100 e power j omega t plus 30 degrees into x cap, and this becomes 20 e power j omega t minus 50 degrees to a cap plus 140 e power j omega t minus 210 degrees is z cap. So if you take real part of it, you get a signal like 100 cos of omega t plus 30 degrees ax cap plus 20 cos of omega t minus 50 degrees ay cap plus 40 times of cos of omega t minus 210 degrees az cap. So you can see here. So what we have here is the same picture which is in phasor form. It looks like this in time domain. So whenever you write a phasor form, you don't see any time variations in the expression. See this expression, you don't see any. This function does not. This electric field does not look like a function of time, right? But does it mean that there are no time variations? No. So any signal which is having time and spatial variations, or it's a vector which looks like this, usually when you write it in phasor form, you remove the time variation, or you write aside that the frequency is fixed, which is 1 megahertz. So you need to understand these conversions because we'll be using our electric field equations and all these things in phasor forms. So let us solve a problem relating to these questions. So you can see here there is a plane wave propagating through medium, and the medium parameters are given, and the electric field is written like this. Electric field is 0.5 times, of course it's a vector, 0.5 e power minus z by 3 sine for 10 to the power of 80 minus beta z, okay, ax cap. So this is a function which is written in time domain. I can see there are time variations, but I can also convert it into phasor form, but we'll see converting the phasor form afterwards. Now what we'll do is uh, we'll try to calculate these questions as the first one is for beta. Beta is simply omega into square root of mu epsilon. Okay. So usually the problem student faces. So till now you have solved the problems which has a cos here, and you said the common format for a wave is something like this: cos of omega t minus beta z. But here there is no cos, there is a sine. So should I use the formulas which I have derived before, or formulas which are given to me? Uh, Means can I take omega as 10 to the power of 8 t 10 to the power of 8, or should I take some other value? There is no need of it, simply because you can see sine 10 to the power of 8 t minus beta z is nothing but cos of 10 to the power of 8 t, okay, minus beta z. I can say minus pi by 2. You can check, okay. So that gives you, if you do this, you get the same number. So it is like it is in the same format, but with some extra phase. I can say there is a minus pi by 2 phase, or simply it's a sinusoidal signal. So if it is not in the general format, you can convert the sine into cos and you can bring it into the general format. So you can see omega is 10 to the power of 8 in this case, and the question asks for beta. So beta is omega into square root of mu naught epsilon into square root of mu r and square root of epsilon r. So that gives you square root of 16, that is a 4. So we get an answer of beta as to solve this problem. So it is 10 to the power of 8 divided by 3 into 10 to the power of 8 into square root of 8 into 2. So you need to solve this one. But before doing all these things, should I use this formula or not? The question is like beta is given some number. Should I use this formula? Why is that case? Why should I doubt to use that formula? The problem here is this is not just a wave. If you can see, the magnitude is not a constant. The magnitude of the wave is varying with z. Here the phase is changing with z, which is good. A wave traveling in positive z direction, but the magnitude is also changing with z, and it is a decaying function. You can see it is along z axis. I can say this is a decaying function along z axis. So whenever it's a wave, so it is a kind of wave, but it is a decaying wave. That's what I can say. Yeah, so if that's my envelope, I can draw a wave like this. So it's a decaying wave. So, oh sorry, I think the diagram is not so good. So let's say decaying wave. So it's a decaying wave basically. So whenever there is a decaying wave, there is an alpha and there is a beta. Where alpha indicates attenuation constant, in fact gamma is written as alpha plus j beta, which we saw. So alpha is an attenuation constant. So you need to have something like e power minus alpha z factor and cos of omega t minus beta z factor. This is a common thing we expect in a wave, where the field magnitude falls off like e power minus alpha z attenuation constant and the phase constant is beta. So the thing here is, uh, what is the formula for alpha and beta? Okay, it's a very big formula for alpha and beta, but we saw some conditions like materials can be classified as a good conductor or a good dielectric material, right? So let me write those things here. So we classified something like good dielectric and good conductor. In that case, alpha is taken as sigma by 2 square root of mu naught epsilon, and theta is written as omega square root of mu. Of course, if it is free space, sorry, 2 by epsilon, and this is also mu epsilon. And whereas for a good conductor, alpha is exactly equal to beta, which is square root of omega mu naught sigma by 2. So I can see from this formula here, the question that e power minus z by 3 is there. So I can say it looks like e power minus alpha z. So alpha should be equal to 1 by 3. So I know the value of alpha here, but which formula should I use? Should I use this one or this one? So to differentiate it, actually the materials are divided using this one. Sigma by omega epsilon is less than 1. Then you go for it's a good conductor. If sigma by omega epsilon is greater than 1, you say it is a good conductor because this is basically conduction current to the displacement current ratio. So it indicates whether it's a good dielectric material or whether it's a good conductor. So in order to, because we don't know what is the material here, right? We need to take a guess. So let me take a guess. Maybe I'll think this is a good dielectric and I'll see. So if I consider this a good dielectric, then the alpha formula should be like this. So it is 1 by 3 should be equal to sigma 2 square root of mu naught epsilon square root of mu r and epsilon. So let me substitute these things. So I get sigma by 2 square root of mu naught epsilon and square root of 2 by 8. So from here I can see that sigma 1 by 3 is equal to sigma by 2. This is 125 and the square root of 1 by 4 is 2. So I can say it is 30, right? So it becomes 1 sigma simply becomes 1 by 90 times pi. I think it's a very small number, but we need to do sigma by omega epsilon here. So sigma is 1 by 90 pi divided by omega is 10 to the power of 8 and epsilon is epsilon naught into epsilon naught into 10 to epsilon naught into epsilon r is 8. Okay. So we'll calculate this one. So to know that we need to know the value of permittivity. So epsilon naught is something around 8.85 into 10 to the power of minus 12, right? So you get 10 to the power of minus 4. So it is like 1 by 90 times of pi, okay, into 8 into 8.85 and get it 10 to the power of 4 numerator, right? So let me calculate this one. So it is 90 times of 90 into pi into 8 into 8.85. So denominator get 10 to the power of 4 divided by 63725. So it is 10 to the power of 4 divided by 63725 into pi. So if you solve it, you get an answer which is 0.499. Okay, so it is a number which is less than 1, right? So this says that sigma by omega epsilon is in fact less than 1 if you take sigma as this value. So our guess is right. So the conductor, so the material is a good dielectric material. So to calculate alpha, I can use this formula. So alpha is nothing but sigma by 2 square root of mu epsilon. And in fact, beta formula can be given like this. So once I have the formulas, I can calculate beta is nothing but omega into square root of mu epsilon. I guess we calculated the answer and you got it as somewhere here, right? So I was calculating it. You, oh, sorry, not this one. I think I erased it. Let me write it again. So beta is equal to omega is 10 to the power of 5 square root of mu naught epsilon naught and square root of mu r and epsilon naught. So it is 10 to the power of 8 into 3 into 10 to the power of 8 into square root of 16. So we get a 4 by 3. So which is 0.374 radian per meter. Okay. Next one is the loss tangent. In fact, we calculate the loss tangent. Sigma by omega epsilon is called the loss tangent. Uh, it's called a loss tangent because it indicates how much this factor basically decides how much amount of losses you are having in a wave, like how much wave contributes to the losses, and it's treated as an angle because this sigma by omega epsilon pushes out how much phase difference you get between an electric and magnetic fields. That's why it's called as a loss tangent. Anyways, we'll talk about it afterwards, but tan theta is called as sigma by omega epsilon. In fact, I calculated it. I think to get an answer some 0.49 or around zero point 0.5 you get an answer approximately. So you can check it out. The next one is wave impedance. So intrinsic in wave impedance is nothing but square root of j omega mu divided by sigma plus j omega epsilon. So omega is given here 10 to the power of 8. Mu and epsilon are mu is mu naught into 2. Epsilon is equal to epsilon naught into 2. Epsilon naught into 8. Epsilon is equal to epsilon naught into 8, and sigma is given here. Sigma we calculated, in fact the value of sigma I think we got something like 1 by 95. So you can use these values here. It's a complex division. You can do it in your calculator. It's easy one to do. So you get an answer something like 177.72 at an angle 13.63 degrees. Okay. So coming to the wave velocity. Wave velocity, how do you calculate the wave velocity is velocity of the wave is nothing but omega divided by beta. So here is omega divided by beta is omega into square root of mu epsilon. That is 1 by square root of mu and epsilon. That is 1 by square root of mu naught epsilon naught into 1 by square root of mu r and epsilon r. So that becomes 3 into 10 to the power of 8 divided by square root of 16. So therefore 3 by 4 times the velocity. Okay, so the next one and the last one, this is a kind of interesting one, is for the calculation of magnetic field. So we know common mistake a student does is the electric and magnetic fields are related by a ratio called eta. So you can maybe write, so from here H is nothing but electric field divided by eta. So I have the electric field expression, so it is 0.5 e power minus z by 3 sin 10 to the power of 8t minus beta z ax cap divided by, I got the answer for eta if I substitute eta. So eta, I got the answer for eta like 117.72 at an angle 13.63. So you might write this as your answer, but this is a wrong way of writing the answer. First of all, there are two mistakes here. The first thing is your electric field direction is ax cap, but your magnetic field will not be in the direction of ax cap. So how do I get the direction of electric field? So E cross H gives you the wave direction. Certain quantum theorem, and we also proved it also, electric magnetic fields and wave directions are perpendicular to each other. So if the electric field is in x direction, and finally your wave should be traveling in z direction, then what should be the magnetic field direction? That simply indicates it's a cap. So here the answer should not be x, it should be a cap. But even though it is still a wrong answer, because you can see the top numerator is a real number, but in the denominator you have a complex number. I already told you, whenever you deal your answers in time domain, the answer should completely a real number, but it should not be a combination of complex and real numbers. So where did we go means what is a mistake here? So the eta you calculated, or the wave impedance which you have calculated, is something which you have done, that is square root of j omega mu by sigma plus j omega epsilon. It's an impedance. So it's actually calculated in frequency domain. So you can't directly divide electric field with eta in time domain. First you need to convert your electric field expression into time domain, sorry, into phasor domain, then you have to solve it. So first we'll try convert into phasor domain. So it is e power 0.5, e power minus z by 3, and sign I will write it in this way, cos of 10 to the power of 80 minus beta z minus pi by 2 ax cap. So the same thing can be written as the real part of 0.5. So same thing can be written as real part of 0.5 e power minus z by 3 e power j 10 to the power of 80 minus beta z minus pi by 2 and ax cap. Right? So you can actually in phasor domain we neglect this e power j factor and e power j omega t factor and real part of it. So finally the phasor form becomes like 0.5 e power minus z by 3 e power minus j beta z and of course e power minus j pi by 2 and ax cap. What is e power minus j pi by 2? It is simply minus j. So I can write this as minus 0.5j e power minus z by 3 e power minus j beta z ax cap. So this is your electric field equation expression in phasor form. I mean this equation here which you see and this equation here, both are same. One is in time domain, the other one is in phasor domain. So now to divide your expression in phasor domain with respect to eta. So eta is nothing but magnetic field is equal to electric field divided by eta. That's wrong. The magnitude of electric field is divided. So what is the magnitude of this field? Right? So the magnitude of this field is, let me clear out some space here. Magnitude of the electric field is, I can see the magnitude is minus 0.5 e power minus z by 3 into j okay. Of course you can also remove j, but what I mean by this equation is when you write it, don't write the vector. Okay, you write the remaining part. Obviously, afterwards, when you write the wave, this extra term should be included. So, in order to remove the confusion, let me write like this. So, you have the electric field. In order to get the magnetic field, you need to have something here in the bracket, and you write the direction, which is a by cap, which we have seen before, how to get it. So, in this one, this factor is nothing but whatever you have here divided by eta. So, it is 0.5j e power minus z by 3 e power minus j beta z divided by eta. Eta is what we got. Eta is 177.72 at an angle e power j 13.63 degrees. So this is your magnetic field, but the expression which is written here is not in time domain. So how do you convert it into time domain? I'll go back again. So same thing can be written as 0.5 divided by 1.77 simply becomes something around 2.81 into 10 to the power of minus 3. And of course this minus j goes as again e power minus j pi by 2 and e power minus z by 3 and e power minus j beta z. But traditionally I have a factor e power minus beta z, and this e power goes to the top. It is e power minus j 13.63 a by cap. So this is your magnetic field in phasor form. So I want to write it in time domain. So if you wanted to write it in time domain, simply multiply the equation with e power j omega t and take real part of it. That gives you the answer. So if I multiply it with e power j omega t and write the answer, so I multiply with e power j omega t, take the real part of it for this answer. So what you can see here is, so this becomes simply 2.81 I'll say milli into, okay, let's not say milli, I'll say 2.81 into 10 to the power of minus 3. And if I add all these exponential ones, you get e power j omega t minus, of course, into e power minus z by 3 power minus beta z minus pi by 2 and of course minus 13.63 degrees. You have to take real part of it. So you get 2.81 into 10 to the power of minus 3 e power minus z by 3 cos of omega t minus beta z minus pi by 2 minus 13.63 degrees. Okay, so cos of something minus pi by 2, it simply becomes, you can tell me this pi by 2, you can write it as sine. Okay, so you can see what happens to the magnetic field is the direction changes, the magnitude changes, and there is some additional phase. So you need to calculate it using intrinsic impedance. So that's it for today. We will see the remaining problems in the next session. Thank you.